If you are picturing an elite athletic heart, you are probably imagining this massive biological pump.
Right, like a huge engine.
Exactly. We have been conditioned for decades to look at an echocardiogram and ask one simple kind of macroscopic question, like how big is the chamber and how much blood is it pushing out?
Yeah, which makes sense on the surface, but that perspective might actually be blinding us to the microscopic realities of human performance.
Right, because we are looking at the volume of the water rather than, the intricate mechanical efficiency of the pump itself.
It is a critical blind spot in traditional sports cardiology. I mean, we are heavily biased toward volumetric measurements, mostly because they are historically just easier to capture.
Sure.
We assess the heart as a basic fluid displacement machine, but we routinely fail to evaluate it as this highly complex biomechanical engine where, the microscopic deformation of the tissue matters just as much as the blood it moves.
Well, welcome to today's deep dive. Our mission today is to take a highly academic scientific look at a really fascinating new layer of athletic profiling.
It really is fascinating.
We're exploring how the microscopic mechanical efficiency of a resting heart, literally how the muscle fibers deform and recover while an athlete is lying completely still, how that can predict explosive anaerobic physical performance on the mat.
Yeah, predicting explosive power from a resting state. It is wild.
It is. And we are pulling this from a groundbreaking research article titled Predictive Effect of Echocardiographic Assessment of Myocardial Efficiency on Martial Arts Performance.
A bit of a mouthful, but a great paper.
Definitely. It was authored by Honghong Song from the Martial Arts Academy at Shandong Sport University and published in the Journal of Sport Science and Medicine, Volume 25, back in September 2026.
And just to set expectations, we are going to maintain strict scientific clarity today. We will be exploring some highly advanced echocardiographic markers, but we will root all of this in the underlying physiology.
Right, because we need to know what we're actually looking at.
Exactly. The goal is to understand not just what these machines are measuring, but why the human heart adapts this way under extreme athletic stress.
Okay, let's unpack this. Let's start with the traditional paradigm, the one we were sort of trying to move past. If you follow sports science or cardiology at all, the standard metric for a strong heart is left ventricular ejection fraction, or LVEF.
Right, LVEF. It is the clinical gold standard for baseline cardiac health.
Right, it basically measures the percentage of blood leaving the left ventricle each time it contracts.
Yeah, it tells you the ratio of the stroke volume to the end diastolic volume. So if your heart fills with 100 milliliters of blood and pumps out 60, your ejection fraction is 60%.
Which sounds great for clinical settings.
Oh, it is highly effective for diagnosing clinical heart failure. But in the realm of elite sports, relying solely on LVEF has massive shortcomings because, well, it doesn't account for energy economy.
Okay, let me use an analogy here. If we rely just on LVEF, it is like measuring a high-performance car's engine strictly by its physical displacement while completely ignoring its thermal efficiency, its fuel mapping, or, how perfectly it transfers power to the drivetrain.
That is a perfect way to look at it.
Right. You could have this massive V8 engine that moves a lot of air, but if it rattles on its mounts or misfires slightly and wastes a ton of heat, it's not going to win a Formula One race.
Taking that engine analogy even further, you can have two athletes with the exact same left ventricular ejection fraction, literally the exact same volumetric output, but the mechanical sequence their hearts use to achieve that output can be vastly different.
Wow, really? So the exact same output, but a different process.
Exactly. One heart might contract with smooth, synchronized precision, while the other exhibits subtle desynchrony. So it's wasting mechanical energy before the aortic valve even opens.
Oh, I see.
And that distinction becomes critical when we look at the specific demands of the athletes analyzed in this paper. We're talking practitioners of Taekwondo, Sanda, and Brazilian Jiu-Jitsu.
Right, because these athletes are not steady-state marathon runners holding a constant heart rate for 2 hours.
Not at all.
The physical reality of combat sports is explosive and erratic. I mean, you are relying heavily on anaerobic lactic and lactic energy pathways.
Yeah, it is all rapid directional changes, sudden grappling entries, and incredibly short recovery intervals.
Exactly. You are going from a resting stance to maximum muscular exertion in a fraction of a second, and then you have to instantly recover your breath to defend the next strike.
What's fascinating here is that when you look at traditional resting markers like LVEF in these combat athletes, the data often looks completely normal or even totally uniform across both amateur and elite competitors.
Wait, really? So you can't tell the difference between a pro and an amateur just by looking at their LVEF?
Nope. It completely fails to capture the nuanced contractile economy, that microscopic mechanical efficiency of the tissue that a martial artist relies on to sustain high-intensity, intermittent output.
Because an elite striker's heart has to be incredibly adept at recovering during those split-second lulls in a fight.
Precisely. And a simple volume metric just cannot measure that capability.
Okay, so if traditional volumetrics are blind to this explosive intermittent power, what exactly is the ultrasound looking for instead?
Well, this paper introduces us to the actual mechanical deformation of the heart muscle, starting with a metric called global longitudinal strain, or GLS.
Okay, GLS, what is that exactly?
While LVEF measures the fluid, GLS measures the container. It quantifies the structural deformation of the myocardium.
Okay.
Specifically, it measures exactly how well the heart muscle itself shortens longitudinally from the base near the valves down to the apex during a contraction.
Oh, I get it. So we are measuring the physical flexing and crunching of the tissue itself,
No.
totally independent of the blood inside it.
Exactly, the actual shortening of the myocardial fibers. Now, there is a crucial scientific nuance from the paper to keep in mind here.
What's that?
Because GLS represents muscle shortening, it is actually measured as a negative percentage. So a more negative value indicates greater longitudinal shortening.
Okay, so a strain of minus 22% represents a more dynamic, pronounced contraction than a strain of minus 20%.
Exactly right.
Now, I bet you might be wondering how an ultrasound can possibly measure the microscopic crunching of tissue without doing invasive surgery. Like, how does a machine track physical deformation in a beating human heart in real time?
It sounds impossible, but the technology used in this study is a highly advanced ultrasound platform called the Vivid E95. It utilizes something called speckle tracking echocardiography.
Speckle tracking. Okay, how does that work?
When the ultrasound waves interact with the myocardial tissue, they scatter, and that creates a unique visual pattern of acoustic markers or speckles within the heart muscle.
Okay.
These speckles act like permanent natural acoustic fingerprints right in the tissue.
Wow. It is essentially tracking a specific freckle on someone's skin as they move, but doing it on the interior wall of the left ventricle.
That is a great analogy. The software tracks these acoustic speckles frame by frame, hundreds of times a second, mapping them across a 17-segment model of the heart.
That is incredibly detailed.
It is. It observes precisely how each individual segment lengthens and shortens throughout the entire cardiac cycle. But identifying movement is only half the equation here.
Right.
To understand efficiency, you have to actually measure the work being done.
And I had to push back here on a mechanical level. Like, movement isn't the exact same as work.
True.
I mean, I can wave my arms around in the air all day, that is movement, but I'm not moving any weight or overcoming any real resistance.
Yeah.
How does the machine know if the heart's movement is actually productive?
Good question.
This brings in the next two metrics from the paper, right?
Mm-hmm.
Global work efficiency, or GWE, and global wasted work, GWW. But seriously, how do you quantify energy that doesn't do anything?
But the genius of this methodology lies in creating a pressure strain loop.
Pressure strain loop.
Yeah. The researchers take the speckle tracking deformation data from the ultrasound, and they synchronize it with the athlete's systemic resistance. And they measure that resistance using a simple brachial blood pressure cuff.
Oh, wow. So they combine the two.
Right. By mathematically combining the mechanical crunching of the tissue with the actual pressure the heart is pumping against, the software calculates the true myocardial work.
So the software is basically calculating the delta between the physical effort of the muscle and the resistance of the circulatory system.
Exactly. And that gives us global work efficiency, or GWE. It is the ratio of constructive myocardial work to total myocardial work.
Right.
It tells us what percentage of the heart's mechanical energy actually contributes to pushing blood out of the ventricle.
And then the global wasted work.
Conversely, global wasted work, or GWW, quantifies the mechanical energy expended by the heart that does not contribute to ventricular ejection.
But wait, why would a healthy athlete's heart waste work at all? I mean, what is happening physiologically that causes energy to just disappear without moving any blood?
It typically occurs during isovolumic contraction and relaxation.
Isovolumic meaning the volume stays the same.
Exactly. These are the fractions of a second when the heart muscle is actively generating tension, but the aortic and mitral valves are still closed.
Ah, okay.
If there is even microscopic desynchrony, meaning one tiny segment of the ventricle wall contracts a millisecond before the rest, that segment is burning energy stretching other parts of the muscle rather than building the pressure needed to open the valve.
Wow.
That is wasted work. It is energy burned pushing against a closed door.
That makes so much sense. Now, we have to talk about how Honghong Song and the research team actually applied this technology, because they designed a truly brilliant stress test.
They really did.
They recruited 180 national-level martial artists between the ages of 18 and 30, but they avoided the classic sports science trap of comparing elite athletes to sedentary office workers.
Right, because comparing a high-level athlete to a sedentary control group will always yield massive physiological differences.
It's too obvious.
Yeah, it provides very little insight into what distinguishes a good athlete from a truly great one. So to solve this, the study created an internal performance reference.
Meaning they compared athletes to other athletes. They took all 180 of these highly trained competitors and put them through a grueling physical testing battery to generate this composite performance score.
Using Z-scores, yes.
Right. They standardized the data using those Z-scores and divided the athletes into tertiles. So they compared the top 60, the higher performance tier, against the bottom 60, the lower performance tier.
And remember, the lower performance group here still consists of national-level athletes training 5 to 6 days a week.
Exactly. We are looking for the absolute microscopic margins of elite performance.
And the physical tests they utilized were designed to isolate the exact energy systems required for combat sports.
Yeah, let's talk about those tests. They used the Wingate anaerobic test on a Monarch peak bike to measure absolute peak anaerobic power, right?
Yes, very brutal test. They also incorporated the T-test for rapid multidirectional agility, the human benchmark for visual reaction time,
The Balance Air Scoring System, or BSS, for postural stability, and the finger-to-nose alternation test, the FTAT, to assess neuromotor coordination.
It was incredibly comprehensive. But the crucial detail of this methodology is the timing.
Right.
They didn't test the athlete's hearts while they were gasping for air on the bike. The physical testing battery was conducted exactly 24 hours after the echocardiographic imaging of the resting heart.
So they scanned them, waited a full day, and then tested them. Why is that 24-hour separation so important?
That separation is vital for scientific rigor. If you perform an echocardiogram immediately following a Wingate test, you are going to reveal a heart in a state of acute, localized exercise fatigue.
Oh, I see.
Its mechanics, its calcium handling, its repolarization, everything is temporarily altered. By separating the resting ultrasound from the maximal exertion, the researchers isolated the pure resting cardiac baseline capacity.
Oh, that makes sense. They wanted to know what the engine looks like when it's just idling in the garage, and if that idle can predict the car's top speed on the track the following day. So they have this pristine, rested snapshot of the heart's mechanics. When they finally put these athletes on the mats 24 hours later, did the ultrasound actually match the scoreboard?
It absolutely did.
Let's look at the physical gap first. The performance differences were undeniable. The top tier produced vastly more peak power on the bike, 11.7 watts per kilogram compared to 9.3 for the lower tier.
That's a massive difference at that level.
And they finished the agility t-test much faster too, 9.0 seconds versus 10.6 seconds. But most importantly, it translated to actual combat effectiveness. The pack group had a competitive win-loss ratio of 82.7% compared to just 56.4% for the bottom group.
So having definitively established that the top tier is superior in explosive power, agility, and actual martial arts competition, the core question of the paper is finally answered by the cardiac data.
Here's where it gets really interesting.
Yeah, the data shows their resting hearts were fundamentally different.
Okay, break this down for us.
Well, the elite group showed a significantly greater GLS magnitude. Their longitudinal strain was minus 22.6% compared to minus 20.4% in the lower group.
So their heart muscle literally deformed and crunched more dynamically at rest.
Exactly, and their energy economy was vastly superior. The elite group demonstrated a global work efficiency of 96.0% compared to 92.1% in the reference group.
Wow.
Even more strikingly, their global wasted work was just 9.4 millimeters of mercury percent compared to 13.2 in the lower tier.
That's huge. So at rest, the elite hearts were wasting significantly less mechanical energy per beat.
Yes.
But why? I mean, what is happening in the muscle fibers of a taekwondo fighter that creates this hyper-efficient tissue?
Yeah.
Why does training for rapid kicks and takedowns result in lower global wasted work when you're just lying on a table?
It all comes back to the physiological demands of intermittent combat. The heart is subjected to sudden, massive spikes in afterload when the athlete strikes, followed by just milliseconds of required recovery. At a cellular level, to survive this, the myocardium has to optimize its calcium ion transport. The myofibrils, the actual muscle fibers, must adapt to snap back to their resting state incredibly fast so the chamber can refill before the next explosive movement.
Wow, so they're adapting to that extreme stop and go.
Precisely. This cellular adaptation to extreme, rapid on and off states results in a highly synchronized contraction. When they are at rest, that enhanced synchronization means virtually zero energy is wasted stretching opposing muscle fibers. Every ounce of effort goes into building pressure.
Which introduces the final piece of the puzzle, right?
Yeah.
A metric called the Myocardial Performance Index, or MPI.
Right, MPI.
It is a composite timing index that looks at the timing of systole, the contraction, and diastole, the relaxation. It measures the duration of those isovolemic phases we discussed earlier relative to the actual ejection time.
And with MPI, a lower number is better because it indicates highly compact, efficient timing of the cardiac cycle.
If we connect this to the bigger picture, what did the stats show?
The statistical analysis in the paper showed a very powerful correlation. A lower MPI, that highly compact systolic and diastolic timing, strongly correlated with shorter t-test agility times and fewer balance errors on the physical testing.
It really makes you think of a tightly coiled spring.
Oh, that's a perfect image.
Yeah, like if the heart's mechanical timing at rest is that compact and disciplined, it perfectly mirrors the athlete's gross motor ability on the mat. The heart can mechanically reset and fire with zero hesitation, just like the athlete can rapidly change direction in a fight without losing their balance or coordination.
Exactly. The microscopic mechanism of the organ is literally mirroring the macroscopic movement of the entire body.
That is incredible.
The cardiovascular system and the neuromotor system are intimately synchronized. A heart that demonstrates mechanical precision and zero wasted effort at rest serves as the biological foundation for an athlete who demonstrates explosive precision and zero wasted movement in competition.
And the researchers didn't just observe these correlations and stop there, did they?
No, they took it a step further.
Right. They built logistic regression classification models to see if they could mathematically predict which performance tier an athlete belonged to, based solely on these resting heart metrics.
And the statistical model proved to be highly robust. They found that when you combine GLS, which is the magnitude of the tissue deformation, with GWE, the energy efficiency, the model could classify an athlete into the higher performance tier with an area under the curve, or AUC, of 0.91.
Okay, for those of us who don't spend our days building statistical models, an AUC of 0.91 basically translates to almost 86% classification accuracy.
Right.
They could predict with 86% accuracy how explosive an athlete was on the mats, purely from looking at the mechanical efficiency of their heart while they were lying still on an exam table.
And what is most compelling about this regression model is what it outperformed.
Oh, yeah.
This resting cardiac model was much more accurate at classifying elite athletes than looking at base covariates like their total training age, their total skeletal muscle mass, or even their body fat percentage.
That's wild. The microscopic mechanical efficiency of the heart was a better indicator of elite explosive status than the actual visible size of the athlete's skeletal muscles.
Exactly.
Sounds like science fiction. So what does this all mean? Can Olympic scouts just roll ultrasound machines into gyms, scan the athletes while they're sleeping, and draft the gold medalists without ever actually watching them spar?
Well, while the data is incredibly compelling, we have to apply crucial academic restraint here, and the authors explicitly outline this in their limitations.
Okay, what are the caveats?
First, this is a cross-sectional observational study. It establishes a strong statistical association, but it does not definitively prove causation or longitudinal prediction.
Right, so we know these heart metrics correlate with elite performance at this specific snapshot in time, but we don't know if they guarantee future success.
Exactly. We don't know the origin. We don't know if years of grueling martial arts training cause the heart to adapt and look like that, or if they were genetically predisposed to have a highly efficient heart, which then allowed them to survive the training and become elite.
The classic chicken and egg problem in sports science.
Yep. Furthermore, these are resting measures. While they correlate beautifully with peak anaerobic power generated a day later, they do not capture heart performance during active combat fatigue.
Ah, true.
Speckle tracking a resting heart doesn't show us what happens to myocardial efficiency in the third round of a grueling match, when lactic acid is flooding the system and the autonomic nervous system is redlining.
So they need more data.
The authors are very clear that longitudinal validation is required. We need to track athletes over several years to see if these resting markers actually predict long-term athletic development before this technology can supplement traditional talent identification.
It really makes you wonder, though, if these microscopic efficiencies in a resting heart can so accurately predict the explosive dominance of a martial artist, what would this exact same speckle tracking technology reveal about other disciplines?
Oh, the possibilities are endless.
Right. What does the myocardial performance index of a freediver look like? Someone who has to totally suppress their heart rate while holding their breath at extreme depths.
Or what about the resting cardiac strain of a chess grandmaster burning thousands of calories through sheer cognitive stress?
Exactly. Are we on the verge of screening all human talent at a microscopic cellular level?
It is a profound frontier. I mean, we are moving from a paradigm of measuring growth anatomy to measuring cellular economy. We are finally developing the technology to measure the hidden engines idling inside us, and it forces us to reconsider the subtle physiological baselines that might be dictating our daily physical and cognitive potential without us even knowing.
That is a lot to think about. For anyone who wants to explore the methodology, the pressure strain loops, and the speckle tracking technology further, I highly encourage you to read the full article by Honghong Song titled Predictive Effect of Echocardiographic Assessment of Myocardial Efficiency on Martial Arts Performance.
Yes, you can find it in the Journal of Sports Science and Medicine.
It is a meticulously designed study that provides a vital bridge between clinical echocardiography and elite human performance.
Highly recommended.
And to make sure you never miss future scientifically rigorous deep dives into cutting-edge research just like this, be sure to follow the channel and turn on your notifications. We started today by talking about how we have always judged an athletic heart by its size, like a blunt mechanical fluid pump.
Right.
But it turns out the secret to true explosive power isn't just in how much blood the pump can push. It is in the quiet, microscopic efficiency of the machine itself. Thanks for joining us, and we will catch you on the next deep